Hello, welcome to the fifth video in the section on vectors. And in this video, I'm going to discuss the vector product, which is another way, besides the scalar product, of multiplying two vectors together. It's distinguished from the scalar product in that the result is a vector. That's why we call it the vector product. Okay, so what is the scalar product? Well, there are two definitions, as with the scalar product or dot product. I'm going to first give a straightforward definition that just tells you how to compute the vector product when you know the Cartesian components of a vector. And it is shown here on the slide. So we have the two vectors A and B with components given by the A with the subscripts and the B's with the subscripts. And then this vector product, or cross product as it's sometimes called because of the notation with this cross, is given by the formula here on the right-hand side. And so this is a complicated formula. There's a few mnemonics to remember it, one of which we're going to go over. But it has a geometric meaning, which we're also going to be covering. But it's good to start out and just know that the cross product is given by this particular formula. And we'll discuss the meaning of this formula as we go through this video. Okay, so as I said, this is also called the cross product of two vectors. It gives another vector with the three components shown here. And one important property of this vector or cross product is that the cross product of the vectors A and B is another vector which is also orthogonal to both of the vectors A and B. So a lot of the applications of the cross product are based on this property. When we want to find a third vector which is orthogonal to two vectors A and B, we can use the cross product in order to do that. Another property of the cross product is that the magnitude, if we take the magnitude of A cross B, that's equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So theta, as in when we discuss the dot product, is the angle between these two vectors A and B. And as I said, there's some mnemonics to remember this complicated formula for calculating the cross product, and one of them uses determinants. And I'm going to discuss that in an example. If you haven't heard of determinants before, that's okay. If you have heard of them, you may have a slight advantage in remembering the formula, but I'll still go over it. All right, so let's look at an example of calculating the cross product between two vectors and discuss how we can remember that complicated formula. All right, so I'm going to write down the vectors. A is 2i minus 3j plus k. We've written the vectors in terms of the three basis vectors, which are parallel to the x, y, and z axes. And the vector B is I plus 2j minus 3k. And we want to calculate the cross product of these vectors and then check that the cross product is in fact perpendicular to both of the two vectors. All right, so let me go back to the previous slide just so that you can see the formula for the cross product. And you can then confirm that it's going to be consistent with what I'm going to show you by a different method using a determinant. And so to calculate the cross product of A and B, we do the following. We write a matrix where the top row contains the basis vectors I, j, and k. The second row contains the entries of A corresponding to each I, j, and k. So we have 2, -3, and 1, 2, -3, and 1. And then the third row contains the entries of B in the same way. So 1, 2, -3. Okay. So now we have A and B written into this matrix, and the determinant of A and B is simply the determinant of this matrix. Sorry, the cross product of A and B is simply the determinant of this matrix. And if you know what a determinant is, then you'll know how to calculate it. But if you don't know what a determinant is, I'm still going to explain. So to calculate the determinant of this matrix, you go along the top row here. And so we first start with I. And then we multiply I by 2 by 2 determinant of this lower right section where we delete the top row and the first column, the row and column that contain I. And the determinant of this 2 by 2 matrix is the product of the diagonal entries, so that's -3 times -3, minus the product of the off-diagonal entries, so that's -2 times 1. All right, so that's what we get as the coefficient of I. Then we continue along the top row, and when you get to the second column, where j is, you always put -j, and then you delete the row that contains j, the top row, and the column that contains j, which is the middle column now, and you then take the determinant of the remaining 2 by 2 matrix. So that's 2, 1, and 1, 3. And so this determinant is the diagonal entries multiplied together, 2 times -3, minus the product of the off-diagonal entries. So that's -1 times 1. Right. And then finally, you get to the last entry in the top row, k. And for the third entry, we write just k. And then we delete the row containing k, that's the top row, and the column containing k, which is the third column, and take the determinant of this 2 by 2 submatrix. And that's going to be the product of the diagonal entries, so 2 times 2, minus the product of the off-diagonal entries, which is minus -3 times 1. Okay, so this is the determinant. And if you look on this slide here, you can check we've actually written down the same formula as what is shown on the slide. Okay, and so let's calculate each of the components here. We have 9 minus 2, so 7i, and then we have -6 minus 1, so that's -7, but then there's another minus here, so that's plus 7j. And then we have 4 plus 3, so that's plus 7 times k. Okay, so the cross product of these two vectors is the vector that just has 7s as all three of the entries. Now the exercise, the example, also asked us to check that this vector is orthogonal to both A and B. So let's do that as well. So in order to check that this is orthogonal, this cross product to A and B, we take the dot product of this cross product with either A or B. So check A cross B is orthogonal to both A and B. First, let's take the dot product of A with A cross B. So remember that these vectors A and A cross B are orthogonal exactly when the dot product is 0. So you can see A there on the slide. So the first component of this is going to be 7 times 2, the first entry of A, plus 7 times -3, plus 7 times 1. So you add these up, you have 14 minus 21 plus 7 is 0. So in fact, A is perpendicular or orthogonal to A cross B. Let's also check for B. So the dot product of B with A cross B is equal to, B is once again written on the slide, and so we have 7 times 1 plus 2 times 7 minus 3 times 7. And so 7 plus 14 minus 21 again equals 0. And so we see that the cross product of A and B is in fact orthogonal to both A and B. And this is always true. The cross product of A with B, any vectors, is always going to be orthogonal to each of the vectors. All right, so let's continue and discuss some of the properties of the cross product. So the first property is that the cross product of a vector with itself is always equal to 0. And if we go back and have a look, remember that the magnitude of the cross product was the magnitude of A times the magnitude of B times sine of theta. And so theta is the angle between A and B. And if A equals B, this angle is 0, and the sine of 0 is 0. And so the cross product of a vector with itself is always 0. Okay, the cross product is anti-commutative. That means that if we switch the order in which we do it, so we change A and B in the cross product, we get multiplication by -1. Remember, for the dot product, it doesn't matter what order you did it in, but for the cross product, you have to multiply by -1. You can see that from the formula from the first slide. The cross product also satisfies the distributive rule. The distributive rule really is what we mean when we say a product. So we have a mapping of two vectors to a third vector, and the fact that it satisfies the distributive rule is one of the fundamental properties that we want when we call something a product. So it satisfies the distributive rule. And one of the geometric properties of the cross product is that A, B, and A cross B form a right-handed system. So what does this mean? So it means that if you take your right hand and you point your fingers in the direction of A so that they curl in the direction of B, then your thumb will point in the direction of A cross B. So if A is up here, B is to my left, then A cross B would be pointing behind me. So you could also consider if you have a left-handed system, then it would go the opposite way, right? So if I curled my fingers this way, then my thumb would point forward. So try that with your own right hand and left hand, and you'll see what I mean by that. It's a bit difficult to visualize probably when I'm doing it. All right, finally, there is this triple product, which is shown here. A cross B dot product with C. This quantity is a product of three vectors, A, B, and C. It's called the scalar triple product. And we have this identity that if you rotate A, B, and C, so here we have A cross B dot C, and then in this next one, we think that we've moved everything to the left. So A has come around, and then B and C have moved to the left. And so we have B cross C dot A, and then C cross A dot B. Those are all equal. And in fact, if you take any other combination, where you take this cross product and you have all three of those vectors involved, it will be either plus or minus the same quantity. And this quantity is the volume of the parallelepiped, or I should say the modulus of this quantity, is the volume of the parallelepiped with edges parallel to the vectors A, B, and C. So you may not be familiar with what a parallelepiped is, so I'm going to try to draw one. All right, so we have three vectors. We think of all their bases as being at the same point, the origin. And we have three vectors. Let's call this one A. Call this one B. And let's call this one C. All right, and the parallelepiped with edges parallel to A, B, and C is what we get when we say take B over to the other side. So translate it here. Put its base at C, and so we have this vector here parallel to B, really the same vector as B, with base at the end of C. And then this would be vector C. And then we take A and put it over here. And then we extend this to a parallelepiped where all of the edges are parallel to one of these vectors. I haven't done a good job drawing A there. So all of the edges should be parallel to one of A, B, or C. This is the parallelepiped that is spanned by A, B, and C. And the volume of this parallelepiped, the volume of this three-dimensional solid, is equal to this scalar triple product. Okay. So let's continue and discuss a bit more about the cross product. one application of the cross product is finding the area of a parallelogram that is spanned by two vectors a and b. So the area of a parallelogram is equal to this base times the perpendicular height, so the height that's perpendicular to the base. Let's put a picture here so we can describe what this means. So here we have this parallelogram with sides parallel to a and b. And so the base, in the way we've drawn it, it would be the length of a, the modulus of a. Then the height is the perpendicular height above a, so we take this dotted line, which is perpendicular to the vector a, and the length of that line up to the top of the parallelogram is the height. The area of the parallelogram is equal to the base times the perpendicular height. And as you can see, this perpendicular height from trigonometry is the sine of the modulus, or sorry, the sine of theta times the modulus of b, and thus the area of the parallelogram is the modulus of a times the modulus of b times the sine of theta. And so the area of this parallelogram, given by the vectors a and b, is equal to the modulus of a cross b. So this is a geometric way to interpret the modulus of the cross product, the area of this parallelogram given by the vectors a and b. Okay, so now we've discussed a few things about the geometry of the cross product, and we can describe the cross product not just using the formula that was on the first slide of this video, but in terms of geometry. So when we have two vectors a and b, the cross product is the unique vector which is perpendicular to the plane containing a and b. So you have two vectors. They describe a plane. They're both tangent to one plane. It's the plane containing the origin and the heads of those two vectors if they're based at the origin. It's the unique vector that's perpendicular to that plane and satisfies the right-hand rule. So remember, you take your right hand, your fingers point in the direction of A so that they curl in the direction of B, then your thumb points in the direction of A cross B, and the magnitude is given by the area of the parallelogram defined by A and B. So this uniquely defines a vector, and that is the cross product of A and B, a geometric description of the cross product of A and B. Okay, so here's a picture. So we have A and B. The cross product is perpendicular to the plane containing A and B, perpendicular to both A and B. It satisfies the right-hand rule, so if you imagine using your right hand here, your fingers point in the direction of A, so they curl in the direction of B, then your thumb would point in the direction of A cross B. And if you use your left hand, it would point the opposite way. But we use the right hand for the cross product as part of the definition. You could design a cross product that followed the left-hand rule, but the one that we use follows the right-hand rule. And the length of A cross B is the area of this parallelogram, which is filled in with the slanted lines. So one little observation here is that if we multiply each of A and B by a half, so decrease their length by a half, then the area of this parallelogram would decrease by 1/4. So you multiply the area by 1/4, and therefore the length of A cross B would also multiply by 1/4. And this makes sense, of course, if you multiplied A by 1/2 and B by 1/2, you could factor both those 1/2s out, and you would get 1/4 times A cross B. Okay, so we'll look at one more example of using a cross product, this time to calculate the area of the parallelogram given by these two vectors A and B. Okay, so we have A plus I minus 2j, B equals I plus 3j minus 3k. The area of the parallelogram that is described by A and B, so looking at the previous slide, it's that parallelogram there, if these are the vectors A and B, is going to be equal to the modulus of the cross product of A and B. So area of parallelogram given by A and B is equal to the modulus of the vector A cross B. This is the modulus of A times the modulus of B times the modulus of the sine of the angle between A and B. Right? And an easy way to calculate this is by using the formula we have for the cross product. So let's calculate the cross product, and I'll use the determinant as I did before in order to remember the formula for the cross product. So we have A cross B. And so if you haven't seen determinants before, you probably haven't yet memorized this, but we'll go through all the details again. And you do this a few times, eventually you remember how it works. So you put in the top row of this matrix I, J, K. You put in the second row of this matrix the entries of A, which are 1, -2, and 0, because there's no coefficient of K. So 1, -2, 0. And in the third row, you put the entries of B, 1, 3, -3. Okay, and so now let's expand the determinant. So we go along the top row. We first have I and times the determinant of this 2 by 2 submatrix here. So that's times -2 times -3, which is 6. And then minus the product of the off-diagonal entries, which is here 0 times 3, or 0. Okay, then we go to J. And when we do J, we want a minus sign. And we delete the middle row here and take the matrix formed by the first and second columns, or delete the middle column, and take the matrix formed by the first and third columns. And so the determinant there is 1 times -3, that's -3, minus 1 times 0, which is 0. All right, and then finally, we have the last entry across the first row, K. We have K times the determinant of this 2 by 2 matrix, so the diagonal entries multiplied together are 3, that's 1 times 3, minus 1 times -2, that's plus 2. All right, and so we have that this cross product is 6I plus 3J plus 5K. And the area of the parallelogram, what we wanted to find, is once again the modulus of this cross product. So this was A cross B, and the area of that parallelogram we're asked to find is equal to the modulus of A cross B, which is the square root of the sum of squares of the components. So that's 6 squared, 36, plus 3 squared, 9, plus 5 squared, 25, and that's equal to the square root of 70. So the area of this parallelogram is the square root of 70, also the modulus of the cross product of these two vectors. All right, so this is the cross product, an introduction to the cross product. That's the end of this first video about the cross product. And in the next video, we're going to discuss some applications of the vector product or cross product.